safety part. There is another change, and I don't know whether this is the difference between WiMAX and LTE or not, but I think this might be in both. This might be in both, but I have told you about STBC, space-time block code, back when we talked about waveform propagation. It was module 4. And we said that if you have multiple antennas, then instead of sending different information on different antennas, if you send something on one antenna and something related on the second antenna, you can do much better in terms of correctly decoding it. So what you do is, if you have two antennas in two time slots, on the first antenna you send S1 in time slot 1, and on the second antenna you put S2 on time slot 1. In time slot 2, which is just following slot 1, basically, you will be sending minus S2 star on antenna 1 and plus S1 star on antenna 2, where star is defined as complex conjugate. So X plus IY, the complex conjugate is X minus IY. So what is X and Y? Basically, X is the horizontal part, Y is the vertical part, and X, IY is basically, because everything has a phase, right? So if you draw it in a 2 dimension, you saw those points in the QAM, right? So they are expressed as X plus IY. Horizontal part and the vertical part. Sine theta and cosine theta. Okay, if the amplitude is A, then A sine theta would be, I think, vertical part, A cos theta would be horizontal part, something like that, right? So theta is the phase. So you put every symbol as a complex number, and you do the complex conjugate, and sometimes you have to multiply with minus, in which case it will be minus X plus, okay? And with some mathematics, it can be shown that this is much better, and this is called space-time block code, because we are doing space. Space is here, antennas are spaced. Okay? Space is antenna, and time is here. Time 1 and 2. And so this is called space-time block code. This was invented by Wahid Tarrok, 1998, and it's basically started a whole new series of STBCs. This is not just 2 by 2. You can have 2 by whatever number by whatever number you want. Whatever number of antennas you have, whatever number of slots you want, you can design some. So, of course. The question is whether this arrangement, like minus S2 star and S1 star, can you arrange it some other way? No. I mean, basically, for every particular size, there is an optimal arrangement. If you arrange some other way, you will get less. So this is the most optimal for 2 by 2. So he's saying the antenna can be arranged in a circular way, and I don't know that, so I'm not going to get into that one. Okay? All right. So same thing, instead of doing on the time, you can do on the frequency. So here's the thing. So we want to send 4 symbols, X1, X2, X3, X4. And now we can send them in this manner. We have X1, X2, X3, X4 and their stars, which means complex conjugate. And we can send 2 of them on one frequency, the other 2 on the other frequency, the other 2 on third frequency, and the fourth frequency. So we are sending 8 symbols on 4 frequencies. Right? And instead of previous diagram, everything was on one frequency, single carrier. Right? In this diagram, we are doing different carriers. Right? So this is a space frequency block code. Instead of space time, it is space and frequency. So on one antenna, there are 2 antennas here. On one antenna, we send this combination. On the other antenna, we send this combination. Okay. You can also do it many different ways. You can do like this, as shown here, where X1, X2 star, X2 and X1 star are like this on 4 different carriers. Here they were on, just like if they were single, this one, right? So there are ways to arrange these symbols and their conjugates. Again, we don't need to get into the details, but the idea is that this increases the noise resistance. Now you are in a much better position to decode these symbols correctly. okay, than without doing this coding. It doesn't increase the rate, you see, because you are sending two symbols in 2 time slots. So you basically, didn't get any rate increase because you have 2 antennas, doesn't matter. But with 2 antennas, now you have much better probability of getting those 2 symbols correctly. Same thing here. You have 2 antennas and you have 4 subcarriers. You're still sending 4 symbols, but you will get much better. Okay, so this is called SFBC. Space Frequency Block Code. So basically, this is how STBC is done on OFDM. Yeah, so basically what it is when you do STBC on multi subcarriers, then you get this. Basically, you are dividing the things on different subcarriers. So here, you see, all we did was x1, x2 star. So what we are saying here is that we are going to do x1 in the first time slot, x2 star in the second time slot, and we are not going to do on the same antenna, and we are not going to do in the same subcarrier the other one, which was x1 star and x2 star. So this is basically mixing frequency as well as the time and the antenna, actually, in some sense. So we have 2 antennas, 2 time slots, 4 subcarriers, everything is mixed in. Okay, 4 subcarriers. Here, we didn't talk about any carriers at all, just one carrier. So that is basically time. So in some sense, this is a special case of the next case where, you have multiple subcarriers. So here we are putting them, and there's a special way, there's an optimal way of putting these. So I'm not going to take you through the mathematics of matrix multiplication and figuring out, which symbols would go where, and then how do you figure out that this is the right symbol which came out. So there is a way to optimally put these signs, and the stars have been put in some optimal way.
No, I was asking what's the difference between the first one and the second.
Oh, what is the first one, second one? Okay, so you see, this is what will go on a single carrier, right? And now it is going on 2 different antennas on 2 different carriers. Here, this is going on 4 different carriers. That combination x2 star minus x2 star x1 and x1 star x2 is on 4 different carriers. Whereas here it is 1 here and 1 here, 2 carriers. This one is a little bit more mixed in. And this one helps if the channel changes fast. So basically, you don't have to wait till the second time slot to decode this. You can just decode it in the first time slot. Now, these are very complex concepts. I'm just giving you a very simple explanation of these, because when you go to read these books, you'll find all the math. All right, now the next concept is puncturing. Puncturing we have done before, but we didn't explain in detail maybe. So basically what you do is, you take some bits and you say, I'm going to put forward error correction on this. So you make twice as many bits. So D1 and D2 is the data bit. And now we added 2 more bits, E1 and E2. So this became D1, D2, E1, E2. 4 bits. Right? This would be called 4 by 2. I mean, basically you're transmitting 4 bits for every 2 bits. Right? But then they say, well, there's no need to send everything. Most likely they will make it anyway. So they do 1/4 puncturing. Means that we will not send 4th bit or 1/4 bit. So they, in this case, they decide not to send E1 and they will just send D1, D2 and E2. Okay, this is called puncturing. So this is 1/4 puncturing, or this basically we wrote a 3 by 4th code, because for every 4 bit we send only 3 bits. Okay. Now, when you get at the receiver, you don't know what the 4th bit was because they dropped it already before transmission. So you put some R1. R1 is not known, right? You put an unknown there. Now, because you have a code, you know that since you have a code, that code will tell you what should R1 be. You can correct the errors, right? So it can correct that and it can say, well, R1 should be that. And then you can get D1, D2 with very high probability, right? Now, they have proven it mathematically that it is much better to do this 4-bit coding and then drop 1 bit than to just do a 3-bit coding. I mean, they could have just gone from here to there, 3x2 code, and then not have to do this R1 business, but they found out this is better. Question?
Is there like an intuitive explanation for that, or is it just is there like a complicated?
No. So the thing is, first of all this coding requires polynomial calculation, which we do actually. The thing is, we do that when we do CRC in 473. I don't know how many of you did the polynomial division in CRC calculation, but I do it in my class. Okay. The same polynomial division is used for all of these coding that we are talking about. Okay. But most of you have not done that, I suppose. And so I'm not going to take that right now. It is, but basically, so just you have taken my word for it that puncturing with a larger code is better than, shorter code. Yeah.
Is it always E1 that's dropped?
No. I mean, that's another math, and I'm not going to go to that one. So puncturing is not just, like that, right? Because the receiver has to know what has been punctured out. So there will be some kind of communication that, okay, I have punctured out the fourth bit, or, third bit or whatever, so that they put it in the right place. That thing. Yeah.
And also, I think that it increases the data rate. Yes?
It does increase the data rate.
Yeah, and I mean, if you want to choose between the E1 and E2, which one do you draw? I think it's just all the time fixed. I mean, like
it's fixed, but what is the question is, that's what I said. It is fixed because the receiver will not know if you just drop second or third.
Yeah.
Then not only you don't know which bit was dropped, you don't know, where to put R1. Right? So that